Welcome back to the Socket Programming in C laboratory series. In the session number 4, we will be covering TCP IP stack and OSI models, TCP working principles, and we will implement a little bit of TCP client server implementation. Alright, so let's dive into details. The TCP IP stack. The TCP IP stack is called the IP stack, Internet Protocol Stack. And it is called so because the TCP works over IP, TCP over IP. The TCP and IP work in tandem to provide end users with a reliable data transfer or communication. As you can see from the OSI model, which I will explain a little bit later as well, we will have 5 layers selected. And in here, at the top, we have the application layer that supports such protocols like file transfers or HTTP that gets the web page for your browser, or remote connection using SSH, and so on and so forth. And then the next one is the transport layer that supports the reliable TCP protocol and connectionless UDP protocol, and so on and so forth. The next is the network layer, where we have the IP, ICMP, IPX protocols that are basically the most used one. The IP is the IP layer, and that is located on the network layer. So here you can see that the transport layer is over the above the network layer, and if you see the connection, the IP layer is located at the network layer, and then the TCP is located at the transport layer. So if we put it together, then we have TCP over IP protocol stack, and that provides the basic communication stack that is used in internet networks. And then down below, it's more detailed, more like a little bit more physical, a little bit complex implementations. The link layer supports the data transfers between two neighboring nodes in the network, for example, a router and your computer. So, for example, how your packets reach the destination. And if you send a packet from your computer to another computer that's located on the internet, then your packet is going to be jumping around routers and other networks. So it will reach its destination because the link layer provides routing protocols and so on. And then the physical layer is just bits on the wire, like ones and zeros being transferred from one node to another. Right. So if you take a look at the TCP and UDP layers that are located on the transport layer, so we are talking about the transport layer that contains TCP and UDP, then basically the TCP IP stack provides us the two protocols that is used commonly in the internet, which are TCP and UDP. And when you're working on your computer and just specifying the TCP socket flow, then it will look like this. Your application will pick the TCP on the network layer, on the transport layer, I apologize, and then it will follow to the IP on the network layer and provide your packet to the link layer, and so on. And if you pick the UDP, then your message will go through this flow. From application, it will go through the UDP and IP and so on. Alright, the OSI model has 7 layers, and it's actually not used, but it's better to understand what are these 7 layers. The first layer is the application layer. That's the top of the stack that supports users and programs that we create. Whenever you create a socket program, that is located on the application layer, and it hides all the difficulties and the complexities of the below layers, the lower layers. So you don't have to be worrying about the other layers when working with this network application. The next one is the presentation layer. It translates between the data format that's coming from the lower layers, and it provides a readable message itself to the application layer. And then you have the sessions that manage the connection, control, and disconnection of the communicating sessions. The next one is the transport protocol that contains the TCP, UDP protocols. If you remember, the TCP provides protocol services to application layer. And a little bit later, you will understand why we need this transport layer. Now I'll explain why. The network layer contained the IP, the IP protocol, if you remember. The IP protocol is referred to as best effort protocol. That means IP will send your packet to the destination, but it does not assure that the packet is being delivered to the destination. The work that has to be done to ensure that your packet is being delivered to the end node, the destination node, is done by the TCP protocol that is in the transport layer. That makes the network layer more stable by implementing the transport layer. I used the wrong word, not implementing. We don't have to implement it. The transport layer is provided by default. You can just pick the TCP. That means your packets will be surely delivered to the destination computer. So the network gets the data all the way from the source to the destination and provides service to the transport layer. That means the transport's UDP or TCP uses the IP protocol to send and transfer the data. And then the next job is to assure that the packet is being delivered to the destination. The next layer, the lower layer, is the data link layer. It provides services to the network layer, and it provides hop-to-hop delivery. As I told a little bit before, it is used by, for example, routers to forward your packets to a proper node in the internet, so that there will be no problems with the network congestion. The network congestion. So the network congestion is stuff that are solved in the data link layer. The network congestion is solved by smartly picking the route through which the packet will go through. And the next lower layer is called physical, that transmits raw bits, ones and zeros from one node to another. And from these 7 layers, we pick the application, transport, network, and data link and physical layers as a TCP IP stack, by which we come to this stack that is most commonly used in internet. Alright, so what is the difference between TCP and UDP? The TCP sockets are referred to as connection oriented. That means they're reliable. They make sure that your packets are being transmitted to your destination. And UDP sockets refer to as connectionless. That means it doesn't really assure that the packets are being delivered. You will just transfer your message to the destination computer and just say just keep on sending the data, and the work that needs to be done to receive the packet is done with the UDP client. So here you can see from this illustration that TCP sends a packet to the destination computer, and then it makes sure that the packets are being delivered with the reply messages that are coming from the destination computer. If you send one packet, then at the beginning the destination computer will say, I received this packet, and then it will jump on to the next packets, and then it will be receiving the confirmation of those packets. So that's how the TCP knows that the packets are being delivered to the destination computer. But UDP does not do that. UDP just keeps on transmitting data. Like, for example, what are the usages? The example for the UDP protocol is video streaming, live video streaming. For example, if you're live streaming a video, then sometimes your video freezes, but after a while it keeps on you keep on seeing the live video after a little bit of pause. That means when the video was paused, there was a connection issue. At that point, the packets were not coming to your computer. Like if you're watching a YouTube translation, then you don't, the connection may be abrupted, the connection may be interrupted for a while, and then it will keep on receiving the rest of the packets. And then the TCP is used in such examples like email, when your message has to be completely sent to the destination. You will not be happy when your email is just like half of your email is delivered and then half is not delivered, right? In that case, you use TCP. And UDP is like video streaming, gaming. Sometimes if you're playing a game, then the opponent might just fly from one place to another place, just disappear from the one location and appear in another location in your computer. That means the locations in between those two in between those disappearing and appearing locations were not received by your computer. So that's where you use UDP, and that's where you use TCP. So that's the basic difference between TCP and UDP. So the TCP, when implementing TCP connections, then you need to implement TCP client and server, and the server's functionality call order, if you remember, it was like this. First you have to create a socket by a socket function call, and then you have to bind that socket to a specific address, and then you have to listen for clients connect requests, and then you have to accept those connection requests. The next thing is you will be communicating through that socket with the clients, and after you finishing those communication actions, you will just close that socket. So that's basically a life cycle of the TCP server. So first, what we have to understand is after creating a socket and then binding, we have to listen for clients to connect, right? And connection requests are a type of data transmission. So one separate socket is required to be open for accepting connection requests. That means we will have to create one server socket, so that's what we call the server socket. Will be waiting for clients to try to connect, right? Then we have a list of, that means like a queue of clients that want to connect us. So we'll keep a list of clients. For example, here we have 3 connection requests in our queue, right? So that is specified by the backlog. So a backlog means the size of the queue that will be waiting for connection requests. And the next one is accepting. So we have the list of connection requests, right, in your queue. So from that queue, what the server socket does is from that queue, it will just pick one, the first client that made a connection request. It will just pick and accept that connection request. A new socket created according to the request data for the requesting TCP client. That means after this function call of accept, we will be creating a new socket with the client socket that try to connect to the server, TCP server, and this will be returning that file descriptor. That means the socket's descriptor. All right, now that we understand what the listen is and what the accepts are, one more thing. So here you can see that the request state is being changed into waiting state after listening, and then after accept, the request state is being converted to connect state. All right, the TCP client has to do a little bit of function calls. It's not that complex as the TCP servers. It's just 4 basic steps. First, you have to create a socket from the client side, and then you have to connect to the IP address of that TCP server. After this, you will have the socket open through which you can make read and write function calls. That means communication. After creating a socket, after connecting to the server, then you can use that socket file descriptor to read and write data. And after doing the message exchanging, you can just close that socket. So basically what we have to remember about TCP server and TCP client is TCP server creates a socket, binds it, listens to the connection requests, and then accepts them, and then it will just read or write messages, and then it will close it. And TCP client does just 4 items: socket function call, which means it creates a socket and then connects to an IP address, creating a connection through that socket, and then exchanging data, and then it just closes basically. So let's continue. And if you take a look at the life cycles of the TCP server and the life cycle of the TCP client, it basically looks like this. The TCP server will be running before the TCP client makes communication requests. That's why first we create a server socket, and then we bind it, and then we run the listen function call, after which the TCP client must make the connection requests. So at this point, when the TCP server has started listening to the connection requests, the client will create a TCP a socket, a client socket. And then it will make a connection request. At this point, the TCP server must call accept function call, after which the connection will be established. When the client makes a connect function call and the server makes an accept function call, the connection will be established. That means the data can be transferred between the two nodes, between the two computers. So that means we can make a read and write function calls on both ends. So when the communication is over, when the client has sent and received messages, and then the same thing was done by the TCP server, we can just make sure and just close those sockets, the client socket. And at this point, I want to make a note that a TCP server has a server socket and a client socket running at this point. So we have to make two close function calls so that the TCP client socket was closed and also the TCP server socket was closed. And then the TCP client will be just closing one socket that was created by itself by making the connect function call. And then there is an iterative approach to accept multiple TCP clients that want to connect to the TCP server. That's one option, that's one way of communicating with multiple clients. For example, you create a socket. Oh, okay. TCP server supports a single client at a time, so you have to the accept function call is a blocking function call. That means when you call an accept function, then only one client will be accepted at this point. So after accept, then you have to call the accept one more time so that the other client could also connect to it. So TCP server accepts the next client after existing connection is closed. Like this is one way, like I told you, this is one way of implementing TCP server. In the iterative approach, TCP server accepts next client after existing connection is closed. So this is just a property of an iterative approach. And then to solve the single client issue, we need to create threads for each client. And also what I mean by solving single client issue means only one client can communicate with the server at once. And of course you have used messengers, for example, like a KakaoTalk or something as like Facebook Messenger, and all clients can communicate with the server like simultaneously, right? That means that the iterative approach does not work with messengers, for example. And that problem can be solved by creating threads. That means you have to run the TCP server concurrently on multiple threads so that each thread will be responsible for communication with each separate client. So this is one solution to the single client issue that will be generated by an iterative approach, so that read and write data will be called in their respective devoted threads. So let's take a look at the life cycle of how TCP server works in an iterative approach. So after socket creation, binding, and listening, we accept a client, communicate with them, and then they close the client socket. At this point, after closing the first client socket, we just jump back to the accept function call again to accept the next client connection. It means that another client wants to connect. So we accept the next client, do the same thing with the second client, and repeat the step one more time, again and again. So that gives us the TCP server's iterative approach. And implementation looks like this. So skipping the first parts, the socket creation, binding, listening steps, we just start with the accepting step, where we are just working with 5 clients consecutively. We are accepting a client connection, and then we are with a while loop, we are reading all the whole message that's coming from the client that we just accepted, and writing back the message that we just received. That means just reading and writing. That means just input and output. The server is reading the message that's coming from one client and writing back to the same client. That's called echo client example. So that's this TCP will be echoing back the message that it just received. After which it just closes that client socket, and the for loop will iterate through it one more time. That means the second client can connect to it. It will do the same thing again, read and write, and then close the connection and just jump up to the next one. And then until 5 clients connect to that server and terminate the connections, this for loop will be running. So iterative approach will be working 5 times here. And then the client, TCP client's implementation looks like this. So while true, after creation of the socket, TCP client will make a connection request. Actually, it's about, like, it's before the while loop. It just connects to that server, and then keeps on writing message, like the one message that was created maybe like a little bit before. Here we are getting a message from a console. We are just reading whatever the client is typing from keyboard. We'll be using the fgets method, and then we are sending that to the server by using this write function call, and then we are reading the text, the message that the TCP server is writing, sending us back after our write function call. And then we are just printing out the server has sent this message after we send the content of this message to the server. So you just make a note that we are first writing and then reading, and the server is doing the reverse. It's reading and then writing. So when the server is reading, we are writing, and then when the server is writing, we are reading. So this will be called 5 times, and then the TCP server will also run this iterative approach 5 times, and both will just finish and terminate its connection. And also, let's come back again to the difference between TCP and UDP. And from the technical perspective, from a programming point of view, the UDP works a little bit different than TCP. And in UDP, we don't have to call listen and accept like in TCP. So that's why UDP is a little bit easier to implement than TCP. Like TCP is not also difficult to implement, but like UDP is more easier, even more easier. So that's the difference from the programming perspective. You don't have to make the listen and accept function calls. And there are just 5 steps to create a UDP server. Unlike the TCP server, it was much more. Here, first we will just create a UDP socket, and then we bind it to the server address, and then we'll just keep on waiting until the client sends a message and just send a reply to that client, and just that's it. So this gives us the UDP client server connection. I should have changed it a little bit. I should have said UDP server iterative approach. This will be iteratively accepting clients and just doing the same thing that the TCP server was doing, like right here. Accepting, writing, reading, blah, blah, blah. Oops. All right. And then, so the 5 steps of the UDP client. First, we have to create a UDP client socket, and then we have to send the message to the server, and then just wait until response. First, I think we have to write a message. Oh, okay, all right. So first we have to send a message to the server, and then wait until the response comes from the TCP UDP server. And we have to do the same thing repetitively, or just like by running multiple UDP clients, and then just close the descriptor and exit. So let's take a look at the life cycle of how the UDP server and UDP client works. So UDP server has to create a socket and bind it first, and then we'll be calling the receive from message. So now just make a note that we have to specify which address we are receiving from. So now we have to know that which client is sending us the message. And then the TCP client will create a socket and send a message here. At this point, the receive from message was blocking the TCP UDP server, so we'll be just stuck here until that client sends us a message, and then when we receive that message, we'll be sending back the reply to the client, and then we'll be doing the same thing again and again, like receiving and sending, receiving and sending. That's why it's called UDP echo, just like TCP echo. And then we send a message, and then we receive the reply that the UDP server has sent us by calling the receive from message, just exactly like the same way that the UDP server was receiving by calling receive from. We receive the message, and then we just close it, or we can just repeat the same step again and again if you want just one client to be communicating with the server. So that's basically it, and now let's try to implement the TCP, just simple TCP client server communication. I will be attaching the source code of TCP, just simple TCP client server code that we will be writing right now. So you don't have to write it yourself, but I could not, unfortunately, I could not find an existing source code for this course that I've previously written, so I will be just writing it right now with you guys. If you want to just write it with me, then you can just follow along my implementation. All right. So actually it's a wrong code, so we'll have to do it again. It's a bad code. So what I'll have to do is I'll have to delete it and create a new source code. All right, so let's create a TCP server.c file and start on implementing that. So first of all, the necessary libraries that we will be using in this TCP server are just make sure that you memorize them is stdioh, and I apologize for the oops, that was c.txt. I apologize for the sound of the keyboard that I'll have to be making. Oops, I think it must be here. Show height, file names extension, sorry. Alright, it has to be a C file, and then we have to open it here. So the libraries that we will be using include stdio, string.h file, stdlib.h file, and then unistdh file, and then the arpa inet.h files. Okay, so let's start implementing the code. Okay, main. So if you remember, okay, let me just put this return 0 here first. So if you remember, the steps of TCP server were first creating a socket. Okay, socket creation, and then binding, and then listening, and then accepting, and then writing. That means communication. Communicating, the next one is closing. So these are the steps that we have to implement so that the TCP server will be fully functional. And in order to create a socket and bind and listen, so what we have to do is we have to create variables that are required. So the first one is variables. So the variables that we are going to be needing are the two socket file descriptors for the TCP server socket and then the TCP client socket. So the first one will be the server socket file descriptor and then the client socket file descriptor. The next one is we have to specify the server's address when we want to bind it, right? So for that we have to have a struct sockadder in, for example, server address, let's say. And then the next address that we have to have is the client's address when we will be accepting the TCP client's connection request. For that, we also have to specify no, we don't have to specify, we just have to have a variable with that has a type with type of struct sockadder in. So we will have the client. So basically what we are implementing is just a TCP client working with a single TCP client. The TCP server that is going to be working with a single TCP client. That's why we're just saying there is only one client address. So for now you don't have to deeply understand the details, and if you're really interested in it, then make sure that you can just send an email or you can come to office and then I can explain you in more detail. Okay, so the next thing is we have to, it's just must in C programming, we have to have some variable that we will be using to specify the size of the client address. So for that, let's say client address length. Oops. And then, so now we can jump up to this TCP socket creation step. So what we'll be doing here is we'll be basically assigning a value to the socket address file descriptor by making a socket function call. And here we will be specifying the either PFINet, or it's totally up to you, PFINet or AFINet. And then we'll specify the sockets type that will be, for now, because we are doing the TCP server, we have to say socket string. That will be that will mean the TCP protocol. And then we just can say just 0, that means the IP. Just that's it. It's basically, you always specify 0 here, it's okay. And then we have to check if the TCP server socket was really created. For that we have to say server socket file descriptor is not equal to minus, or you can just say if it's -1, then it is an exception. So we have to print that okay, socket create, okay, failed to create, okay, socket. That means we could not create a socket by making a socket function call. And then we have to just exit with an exit code of 1. That means there has been an exception. Otherwise, it has been successful. So socket has been created. Socket is this number. That will be server socket file descriptor. So after this step, we have successfully created a socket that we could use for binding step, for the next step binding. So let's just bind this server socket to an address, to the server address. And in order to bind the socket to an address, we have to first specify the address. So for that, we have to say server. First, we have to zero out the content of this structure. For that, we use b0, the standard function that is used for zeroing out all the bytes. So we should say server address, and then we have to say size of the server address. And now we have to set the server addresses fields. The first one is the SYN family, if you remember from the previous session. So the SYN family will be the AFINet field, because we're using the address family of internet, that will be IPv4. And then the server addresses, SYN address as address field. That means the IP address will be listening to any client's connection. So we'll be using this inet any to not inet, inether any, to say we want to be accepting any client's connection on any interface in our computer. And the one thing that we should not be forgetting is we have to put this inether any inside the HTAONL function call. If as you remember from the previous session, it means the host address, which is inether any, should be converted into a network ordered address. That's host ordered address that we have to convert to a network ordered address. And this is an IP address. That's why we said L. That means long. And then we have to specify the server addresses port. For that, we have to say SYN port. That will be also assigned with a similar function as H2O and L. But instead of L, we'll be calling S short. I mean, that stands for short. H2N for S. For example, let's say our TCP server will be running 4567 or whatever port that you want to use, whatever port is available on your computer. And in order to not to confuse, let's say we want to use 4444, just for fun. And now we have to bind that socket, server socket file descriptor to this address, to this server address. For that, we have to make a function call called bind, right? But we have to make sure that there will be no problem with binding step. That's why we have to check the result of this bind function call. For that, what we'll be using is we'll put this bind in an if, and then we have to check that this result of this function call is equal to 0. It must be equal to 0. If it's equal to 0, it means it's successful. If it's not equal to 0, that means there has been an exception while binding the server socket to this address, to this server address. And it will be accepting the server address and the oops, I apologize, I just confused it. The first will be the server socket file descriptor. And then we'll be specifying the socket address, the server address, the TCP server address, as the second field, and then we'll be saying the size of this address is actually this value. And then the next thing is we have to change the type of this variable, because we cannot just simply specify it here. We have to change it back to a pointer. We have to take the address of the server address variable, and then we have to convert it into a struct sockadder pointer. It has to be a struct sockadder pointer so that the bind function call could read it properly. And then we have to we can just print out like the same way as we're doing here, but instead of socket creation, we'll just say fail to bind, let's say, and then just exit with a one exit code. And then the next one will be else, like right here. It will be saying bound. So by far, we have written socket creation step and then the binding step. And now we can move on to the listening step. So at the listening step, what we have to do is we have to make a listen function call. Like if you remember, oh, apologize for the K. We have to make a listen function call. And again, we have to make sure that the listen has not faced any problem. And to do that, we have to put this one also in an if, and then say the result must be 0. If it's not 0, that means it has an exception. So the arguments of the listen are going to be the server socket file descriptor, because we have already attached the address to that server socket file descriptor. We can just simply use the file descriptor from now on. And then because we're working just with a single TCP client, we can say the backlog will be just one. There will be just one queue. That's it. We don't want any other client to be in that queue. And then we'll be just printing out that the if it's not equal to 0, if the result of this listen function call is not equal to 0, then we'll be printing out that there has been a problem with listening. List failed to listen. And then we have to exit with a result code of 1. And then here, otherwise, if it was successful, that means the result of this listen function call is equal to 0, we'll be saying, okay, listening. So the next step is to accept that client socket that was put into a waiting state from a connection request state, from requesting state, and that one will be done exactly the same way as a listening step. But first, what we have to do is we have to zero out the client address, just exactly like we did here. We have to zero out that address because we will be loading the client's address into this field at this point. So what we have to do is we have to call this b0 function call first, and we have to specify the client address, and then we have to specify the size of the client address. So done. So now we have zeroed out the client address. Now what we can do is we can just accept the client socket that was put into waiting state by calling accept function call. So when we are accepting, oops, we can implement this way, but actually let's not make our life complex by making like double, triple brackets, but instead let's just say like client socket file descriptor is equal to here. Just let's accept it first and then say client socket file descriptor is not equal to -1. Alright, if it's equal to -1, so the client socket file descriptor will be equal to -1 if the client connection was not able to, if we could not accept the client's connection. So we could have implemented like this to be more like to look more cool, like just in one line, but it would make our life a little bit more difficult to understand. That's why let's just make it separate lines. Load it first here, and then just check it here. So the accept function call is going to accept the server socket file descriptor, through which we will be accepting the, we'll be creating the socket file descriptor, and we have to load the value of the client's address. At this point, we have to provide a the address of the client address variable right here as a second argument that will be stored just like we've done in here. We have to specify the address of that variable, and then we have to convert it into a struct, so cadder pointer. Oops, I just forgot this K. And then the next thing is we have to know the address of this, the size of this client address. That means it can be an IPv6 or IPv4, and which have like different addresses, which have different sizes, I mean. For that, what we have to do is we have to specify the address of our specifically created client address length variable right here. That's why we needed it. So we'll just paste it here. So accept is getting 3 parameters, like I've told you in the first two laboratory sessions. The first one is the server socket, the next one is the client address, the third one is the client address length. Oops, sorry for being so monotonous. I hope you're not asleep at this point. Let's keep on going. So at this point, the client has successfully connected. But if it's equal to -1, that means the client's connection has not been established. So this is an exception case. We have to say failed to accept client's connection. Oh Jesus, we can just say failed to accept. That's all. And then otherwise, if it's not equal to -1, that means the client socket has been established. So we can just say accepted. Oh, I love this word, accepted. All right. Okay. So the connection has been established. The next things are very simple. So we can just write a message to a client and then just close the client socket and then the server sockets, the 2 sockets. So at this point, we have the client's socket open. So we have that door through which we can just then send them just through a message and then receive another message from the client and so on and so forth. At this point, what we'll do from the server side is we'll just write a message, and then from the TCP client side, we'll just receive it. So for that, we have to have a char, for example, char pointer message, that was an MSG, that will contain hello world for the first time that we are working with the network program. So this will be our hello world example. Oops, congrats, so today is your hello world day. Okay, so let's send this message. So for that, we will be using write function call, where we will specify socket file descriptor. Okay, socket, oops, apologies, client socket file descriptor. I keep forgetting the names of the variables that I just created because there are a lot. I don't want to just scroll up and then see the names of the variables. I'm a little bit lazy. Don't be lazy like me. It's a bad habit. And this, as a second argument, we have to say the MSG is the one that we want to send, and then the length of that message is strlen MSG. So we want to send this portion of this message. That means complete message. We will be sending this hello world completely by making a write function call. At this point, we can just print out printf this message has been sent. Or just, why am I making our lives complex? Why don't I just make like sent? So this message has been sent, MSG, and we can just close that client socket file descriptor. And we have to do the same thing with the server socket file descriptor as well. And you just make sure that we've created one server socket here and then the second client socket right here. So we have to close both of them, client socket and then the server socket. So I hope that we are done with the TCP server, and if there are any bugs, we'll fix it later. The next step is to create the TCP client, which will be much easier. Oh, let's not copy and paste. Let's create another file. Okay, TCP, let's call it TCP client.c file. Alright, so the TCP client file will be also containing the same libraries that we have written here. And also, it will contain the same steps as the TCP server, like create socket. Was it like this simple? Socket creation. Oh, sorry. I want to be consistent. Let's say create a socket, socket creation, and then connecting, and then we have to be reading, and then closing. So this is just simple 4 steps. We have to create a socket, connect to the server, and then read a message from the server, and close that TCP connection, TCP socket. So here we have to also have variables, because the reason is the TCP client must know the address of the TCP server that it wants to connect to, and also it has to have variables to store the socket that's being created here. So the first thing that we want to do is we have to create a socket FD. Let's say we'll just, because in the TCP client case we will just have only one socket, that's why we don't have to say server socket and client socket. We literally just one socket with the TCP server, so we have only one variable for it. And then we have the address that will be saying socket in, and that will be containing the address that we want to connect to. And also, okay, we don't need anything. And then the next step is to, don't be lazy like me, but I want to copy and paste. Let's copy and paste this one. So we'll be creating a socket just like we did in the TCP server, but instead of saying server socket, we'll be just saying socket file descriptor. That's it. Fail to create a socket if the socket could not be created. Otherwise, it prints out the socket file descriptor. That will be, I believe it will be 3, because like I told you, it will continue keep on from the input-output socket file descriptors, like keyboard and monitor, the console. And then the next step is to make a connection request that will be made. That will be also not very difficult to do. In order to connect to a server, first what we have to do is we have to specify the same family, just like we've done previously. I want to copy and paste this one as well. Sorry. Don't be lazy like me. It's a bad habit. Don't do what I'm doing, but I can do, basically, because I understand what I'm doing, that's why. And hopefully when you know what the meanings of each line of code is, then you can just copy and paste this for yourself too. Because why am I saying don't copy and paste? Because it might confuse you. It might confuse you on writing like big lines of code. If you copy and paste, then you might not remember what you were doing at a specific line of code. That's why just keep on writing from plain. So what we're doing here is we're just clearing out the server address variable, and we're setting all the bytes to 0 first, and then we're specifying this in family that will be exactly the same as in the TCP server, because the IP address is IPv4, and then the S address is actually specified by, we have to specify the specific IP address. We cannot say IP address any, in address any like here, but instead we have to say inet address, and we have to specify the dotted notation IP address, like I've told you a little bit before. If you remember, it's an alternative to H2ONL, where the long was converted into a network ordered address. So it's doing the same thing, but with the dotted notation IP address instead of just long variable. So we have specified the server address, and now what we have to do is we have to connect to that IP address. And then when making this connect function call, just like we've done in the TCP server, we have to check if the connection was completely established, it was successful. For that we have to also put it inside an if, and we have to say the result should be equal to, it should be equal to 0. If it's not equal to 0, then we have to print out that connection could not be established. Fail to connect. So at this point the connection could not be established, so the client should be exiting with an exit code of 1, that means failure. Otherwise, if the connection was established, then what we have, I'm so lazy, sorry. Don't be lazy like me. Alright, the socket file descriptor is right here. So otherwise we're printing out the socket file descriptor. And then the next step is actually reading what the TCP server was writing right here. So yeah, we don't have to do all these complex stuff. So if you notice, TCP client is pretty simple. We just create variables, create a socket, connect to the server, and just read. That's all. And then we just can just close that socket. So in order to read, what we need to have is a memory area where we will be loading the message that's coming from the TCP server. For that, we will be creating such a thing called a buffer. So buffer will be having a char array. So we have to specify the size of the buffer. For example, let's say for the beginning it will be 128 because the length of the message is just 10 bytes, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oops, I apologize, it's 12. So it pretty much fits in here. We can just say like 12 or 13, it's up to you, but for now I want to say 128. Well, it's my computer, I can do pretty much what I want, right? Alright. So we have to read the message that's coming from the TCP server by making a read function call and specifying socket file descriptor, because we are going to be reading a message that's coming through this socket, and we're saying load this data that's coming from this socket to this buffer, and this buffer contains can store this length of data. So we're saying you can store this read function call can store 128 bytes into this buffer, and actually, this read function call is returning an integer that specifies how many bytes were actually read from the socket. But for now, we don't need to worry about that because we will be diving into details a little bit later in the next sessions, but not today. It's just simple implementation, right? So let's print out the message that we received. The received message will be printed out a not decimal string, like this. So we are printing out the content of the buffer after filling it out with the message that we've just received through the socket file descriptor. Now we can just close that socket file descriptor. After closing, let's print out just like here. Oh, we have not printed out, sorry. So after printing out what was sent, let's just print out in the TCP server part that the sockets were actually closed. Okay, client socket closed, and also the server socket closed. And the same thing will be done right here as well. We'll say that the socket has been closed. So I believe and I hope that we have finished with the implementation of the TCP client and server. So let's now try to compile them and run them. I hope it'll work. Okay, so let's just copy these source files and paste it inside the CYGWin home and your username right here, and then open up two CYGWin terminals. All right. So this console at the left side will be running the TCP server, and then this console on the right side will be running, oh, let's make it like on top of another one. So the console that is below is going to be running the TCP client. So this one will be TCP client, and this one will be the server part. For that, we have to first compile it, gcc-o server, and then tcp server.c file. So we have just compiled, oof, no compilation errors. And then the client will have this command line. Client tcp client.c file. Oops, we have a lot of mistakes. I forgot to fill out the content of the connect function call. Sorry for the confusion. Yeah, that's what happens when you try to explain stuff really fast. Sorry for being fast. You can just slow down the video, and from the next time I'll try to explain it a little bit slower so that I wouldn't make mistakes myself again. So at this point, when you want to connect to that server, you have to say that we are using this socket file descriptor, and then we want to connect to this address. that has this length. But instead of just simply providing that variable, again, if you remember, we have to change it to a pointer to this variable. And that is done by providing the address of this variable, converting to the address, and then converting that address into a struct sockheader pointer. Okay, we can just close it. And now try it again. And we have one more warning. And you don't, oh, I just left print. It will work, but still, let's change it to printf instead of print. Where did I make just print? Where did I put, okay, here, printf, where else? I think that's it. Okay. All right, we're good to go. Let's pretend that this didn't happen, like everything was good. And let's run the server code here. So as you can see that the socket has been created, that means the server socket has been created, and it has a descriptor of 3, and then it was bound, and it is now listening. Now, what the client has to do is it should make a connection request that will be shown in a lifecycle like this. So after listening, the server is waiting for a connection request, which will be running the accept function call. So when we make the connection function call, it will jump up to the read and write lines. So now what we have to do is we have to run the client code as well. So when we run it, voila, the message that was sent by the server is, oh, so you can see after listening, the client made a connection request. Oops, why did I make it to, we'll just figure out a little bit later. So the client has made that connection request, and then the connection request was accepted, after which the TCP server has sent hello world message, and the client socket was closed, and so was the server socket. So here we can see that the message was received and then printed out successfully, and the socket was closed. So we have an issue with the TCP client that was printing out the same line twice. Let's see why. So we are printing it. Oh, this is what happens when you copy and paste. You see, we are printing out the same thing here, and then we are printing out the same thing here. We didn't complete the connect function call. So the thing that we will be printing out here will be actually connected. So the client will be printing out just connected. So that's my mistake. I just copied and pasted and I made a mistake, you see? So don't do it. And on the TCP server part, we forgot the new lines right here. And that's why we are seeing a bunch of trash here. So let's run it one more time and then see everything clearly. So server is running, client is running. Now we see it's been accepted, and the client socket was closed, server socket was closed, and here socket was created and then connected and then received and then closed. Alright, so I will be attaching these source files to these slides, so don't worry, you will not have to write everything yourself. Alright, let's continue. After implementation, now we'll take a look at the TCP echo client implementation, and we don't actually have to implement it ourselves, so we'll just see these slides. So what echo client will be doing is it will be continuously reading the server, actually the above part is this TCP server part, and below part is the TCP client part. The TCP server will be continuously reading the messages that are coming from the clients and then writing back the same message to the client itself. That's why it's called echo. It's like echo is like echo, 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 echo. So that was like a preview echo demonstration that I've just made. Like echo is something that comes back to you right away. The server will be only sending back the message received without knowing the real length and blah blah blah. It will just read the message and load the length of the message that we just received and writing back the same thing to the client. And what client will do is it sends a message first, and then it will receive that message back and then just print out whatever it does, like printing out or sending to someone else. It's just up to them. So if you write these lines instead of what we have just done in our example, like here, for example, let's open up the TCP client part. So instead of just reading the message that's coming from the server, if you write the message and then receive it, and on the TCP server part, if you, oops, it's not colorful, I don't like text without colors. If you, instead of writing, simply writing, if you read the message first and then write back, then you have echo client. So basically that's what you need to know about echo client example. All right. So solution is just put read function in a loop. So the problem here was, I didn't explain you the problem first. The client will be sending specific message, so client will know the length of the message. So the client is sending, for example, hello world. It knows that the length of is 12 bytes, right? Because there are 12 characters. The client knows the length. But the server is actually receiving the message, and without knowing the length, it's sending back the message, and we're just saying, I want to receive the data that whatever the client is sending us. We don't know the real length, and there could be cases like maybe the server will have to receive a file that's coming from the client, for example, 1 megabyte of file, and it will not be, of course, fitting to 128 byte buffer, right? In that case, what we have to do is we have to put a read function in a loop first and read until the end. For example, when we are reading a message, what we'll be doing is we will keep count of how many bytes were read at when we call the read function once, and then we will be adding that receive count into another counter variable that will be the receive total length. And while that receive total length is less than the what we sent previously, that means it's not yet, we didn't completely receive the complete message here. In the previous case, the client was sending the length of the message and then receiving without knowing the real length. Actually, it knows the length, but it's just depends on the buffer size, right? It depends on the buffer size. What if your message is like just 128 bytes and your file length is 1 megabyte? You receive the rest of the file because your buffer size is small. That is solved with this example. So you're writing the message and then counting how many total bytes were received, and until that total number of bytes were received by read function call, just keep on looping because the server will send back us. And then when it's done, we're just saying the end of the message is received length. We're just putting 0 so that the printf will know where to stop printing out the characters. And then we're just printing message from server is this. All right. So we are done with the echo client example. At this point, we'll be moving on to the working principle of TCP. We have to take a look at a little bit more details of how the read and write works. The first thing we have to know is the TCP input-output buffers. I've told you a little bit earlier that we have to create buffers, like in the TCP client case, we had this specific buffer, right? That is actually a buffer on the application layer. It's not the real buffer that is being used by TCP. It's the buffer that is being used by us. So there is one more buffer that is being used internally by TCP when you call read and write. So for each socket, for each input-output, there will be a buffer for each separate TCP. So that means you will have two buffers, right? The first buffer is for yourself, for the application layer, to split out your message into smaller parts and then send or just receive the complete message part by part. And also that small part will be also put inside a TCP's small buffer. Smaller, like it can be smaller, it can be larger, it depends on your number, the number that you specify for your buffer. So the TCP has its own internal input-output buffer. And input-output buffers are automatically generated for each socket creation. Whenever you create a socket, you will have two buffers for input and output. After closing a socket, the last piece of data is left in the output buffer. So that's why you have to also know, like by intuition, that if you close a socket, then there will be an information left over inside your buffer. And if you go into advanced computer networks programming, then you will be handling those last pieces of data inside those internal TCP buffers as well. After closing a socket, the data in the input buffer will be clear. So that's the difference between the output buffer and input buffer. When you close a socket, the output buffer's data will be left there, but the input buffer's data will be cleared out. It will be 0. And such buffers are present because they can be applied in the sliding window technique, as the length of the data isn't predefined neither for input nor for output. That means you don't know how long data you're going to be sending or receiving. That's why you have to slide your buffer through data so that you could receive complete amount of data. That's why TCP provides its internal input and output buffers. All right. Oops, sorry for this unclear text. The format is a little bit weird. So TCP works on three-way handshaking technique. That's very important thing that you have to know. For example, if there are two ends, for example, client and server, when client makes a connection request, it's just like the connect function call. What it first sends, what kind of packet it sends is the first packet will be a synchronized packet. It will send a synchronized packet to the server, and the server will acknowledge that packet. And then it will send the sequence of the packets that the client will be sending. And also the server will acknowledge that the sequence of that packet. It will acknowledge that, for example, the data was sent with 10, including this packet was sent including 10 bytes of data. The server will say, I'm waiting for the next byte that will be 379th byte, right? Just like it was in this one as well. It was just sending 1 byte data with the sequence number 368. I'm waiting for the 369th packet, and then it's sending 369th packet with 10 bytes of data. It's saying, I'm waiting for the 379th sequence number. That means you can refer to it like bytes, just simply. It's the or you can say it's the packet number. So the packets will have their own numbers that will be used by sequence keyword. And the next thing what client does is it sends the 379 packet with 10 bytes of data, and it will acknowledge that packet. So that's how the TCP works. It sends a packet and then it waits for the acknowledgement. That acknowledgement says, I received this packet. So you can send the next one. And the same thing with the server too. After connection establishment, server might want to also send a packet with its own sequence number, and the client will also return back with an acknowledgement packet. It will be vice versa. So start of TCP connection, the client requests a connection by sending synchronized message to the server, and then the server acknowledges this request by syn plus ACK back to the client. So just like this, hi, I want to send a message to you. Okay, you can send me to, okay, thank you. It's like this. And here's the connection establishment, TCP working principle. So these fields are utilized for connection establishment. When computers communicate via TCP, received packets are acknowledged by sending back a packet with acknowledgement bit set. Sequence is the sequence number of the current packet. So you send a packet with a sequence I just explained to you. I'll explain one more time. Alright, let's just say we just explained it. It's the same thing that I just explained previously. So here is the error case. I just sent sequence number 1200 with 100 bytes of data, and then it's waiting for the next packet, 1301, and then this packet was not delivered. For example, sequence of the next packet that this host B is waiting for the host A, 1301. it was not delivered, for example, due to a network congestion. So what the host B did not do is it did not acknowledge that packet because it did not receive it, right? And what host A does is it waits for a specified time, specified interval that's called timeout. So when the timeout expires, that timer expires, what it does is it sends back the packet for which the host A did not receive acknowledgement for. So that way TCP provides a reliable communication. So the host A will know that the packet was not delivered to host B because it did not acknowledge that packet. All right. So the formula is like just like the acknowledgement is sequence number plus the number of the size of that byte data. Acknowledgement: when computers communicate via TCP, received packets are acknowledged by sending back a packet with an acknowledgement bit set. All right, when the connection is being finished, this kind of sequence is being called. The fin flag, like instead of synchronize flag, we'll be using fin flag to finish the socket. That means just closing. When you close the socket, then the fin packet is automatically sent, and here you can see the packets that are being transmitted between the initiator and receiver when the close function call is called. So first, the host that wants to close that socket sends a fin packet, and then the receiver will acknowledge that finishing packet, the fin packet. It will acknowledge that packet, and at this point, it will be the initiator will be waiting for the receiver to also send back the finish packet so that it could also close, and then it also sends back, and the initiator will send back an acknowledgement. That means, okay, I want to connect, I want to close this connection. You can say, okay, all right, so I'm just preparing, I'm going to send back right now the finish packet, and then okay, I want to finish the packet. Me too, I want to finish the packet, the socket as well. I want to close the socket as well, and then say, okay, all right, so we can both close now. At this point, the both hosts will have closed down that socket. That is a way how TCP socket is terminated. And that is it. Thank you for paying attention. I hope to see you soon finally after this all situation stabilize. Wish you best of luck.